Hey guys, today we're going to talk about matrix multiplication. So whenever you think back to adding and subtracting matrices, you may think that with multiplication, you're going to be able to just multiply each element by its matching element in the second matrix. However, this isn't the case. So you're going to need to pay special attention to this lesson. And also, I would suggest the first thing you do is just pause the video and write down all of these notes because you're definitely going to need notes on this. And then once you get the notes written down, you can unpause and we can talk about it a little bit. So the first thing that you need to know is to even be able to multiply two matrices, the number of columns in the first matrix must match the number of rows in the second matrix. So with that being said, they don't have to be the exact same dimensions, but if you have, say, matrix A times B, and matrix A is a 2 by 3 matrix, then whenever you're multiplying it by matrix B, then the number of rows in matrix B, so like the first dimension, must match the number of columns in matrix A. And then whatever number of columns matrix B has is fine as long as these two inside numbers match. So for that reason, so say that like matrix B was a 3 by 1 matrix, so it has 3 rows and 1 column. For that reason, though, matrix multiplication is not commutative. So if you remember the commutative property, that would be saying that like A plus B equals B plus A, or A times B equals B times A. That is not the case for matrix multiplication. A times B is not going to be the same thing as B times A. Because if I switched these two matrices and I tried to multiply a 1 by 3 matrix times a 2 by 3 matrix, then, and that first one, I meant to say 3 by 1, actually, a 3 by 1 matrix times a 2 by 3 matrix, then these two inside numbers, they're not the same. So you can't even multiply B times A. So continuing on, a single element in the product matrix or the resultant matrix is found by multiplying a row of the first matrix by a column of the second. And the single element, that's going to be called a dot product. So that's how you find it. And I'm going to show you a little bit more about that in a second. And then the resulting matrix is going to have the same number of rows as the first matrix and the same number of columns as the second matrix. So using my initial example up here, if I had a 2 by 3 matrix and it was being multiplied by a 3 by 1 matrix, then my resulting matrix is going to use the number of rows from the first and the number of columns from the second. So even though these two matrices, the 2 by 3 and the 3 by 1, might be kind of big matrices, the resulting matrix is only going to have 2 elements in it. So keep that in mind as you're going through these as well. So then I put just an example down here of multiplying two 2 by 2 matrices. So we have to find each of the elements in this. So I said that you're going to be multiplying a row of the first matrix by a column of the second matrix. So this is where you have to pay special attention here. So you have to match the 3, so the first number in the row of the first matrix with the first number in the column of the second matrix and multiply those together. So we would have 3 times 1. And then to that, we're going to add the second number in the row of the first matrix by the second number in the column of the second matrix. So that's going to be plus 4 times 3. So then that's where you see that 3 plus 12, and that was times right there too. It looked kind of like a subtraction symbol, but it was just the multiplication dot. But that's where you see this element here, the 3 plus 12. So for each element in the resultant matrix, it's going to use the row that's in that position of the first matrix and the column that's in that position for the second matrix. So that would be the first element. Like this is how you find the first element in our product matrix or our resultant matrix for these 2 by 2 matrices. So then I'm going to erase this and I'm going to go ahead and do another element. So if I want to find the element that goes in position row 1, column 2, then what I'm going to do is I need row 1 from my first matrix and column 2 from my second matrix. And now, just like I did last time, I'm going to multiply the first number from my row of my first matrix times the first number of the column in my second matrix. So I would have 3 times 5. And then to that, I would want to add the second number in the row of my first matrix times the second number in the column of my second matrix. So that is 4 times 7. And so that 3 times 5 gives you this 15, and the 4 times 7 gives you this 28. So then I'm going to erase it all again, and I want to do this for my second row. So to find the number that goes in row 2, column 1, I need row 2 from my first matrix, column 1 of my second. And I would do that 2 times 1 plus my 1 times 3. And then that gives you this 2 plus 3 here. And so then the last element that I need to find is it's going to be for position row 2, column 2. So I'm going to use row 2 from my first matrix times column 2 of my second matrix. So I'm going to have 2 times 5 plus 1 times 7. And so that's where my 10 plus 7 comes from. So then you just have to simplify this whole thing out, and that'll give you your resultant matrix of 15, 43, 5, 17. So since we're 7 minutes in and we've only done one example, you should be able to see at this point that this is quite a process. It takes a lot to be able to multiply these out by hand. So I want to be able to show you how to do it in the calculator so that you know that you can do it in there, even though I need you to know how to do it by hand as well. So I'm going to pull up my calculator app here, and we're going to do it in the calculator app so that you can see how to do it. If you don't have a calculator at home, there's plenty of matrix multiplication things on the internet. You can find one like that. But I really want you to see how to do it in the TI-84. So if you look on the inverse button, then right above it in blue, it says matrix. So that's where we're going to go. We're going to go to second inverse, and that's going to take me to my matrices. And then I need to enter matrix A and matrix B. So I'm going to come over here to edit and then press enter on matrix A. The first thing it's going to ask is for you to fill out the dimensions. So the first spot, you need the number of rows in matrix A, which is 2. And for my second spot, I need the number of columns in matrix A, which is also 2. And then you just enter each of your numbers. So I have 3, 4, 2, and 1. And after each number, you would press enter, and then we have matrix A there. Now I need to enter matrix B, so I'm going to go to second inverse again, and I'm going to come over to edit, scroll down to matrix B, and press enter. This one also has 2 rows and 2 columns, and now I just need to enter each of my numbers. So I have 1, 5, 3, and 7. And then now all I need to do is actually perform the multiplication. So I'm going to once again go back to my matrix, and I'm going to choose matrix A, and hang on, we're going to go to the matrix, and I need to get matrix A in my calculator. There we go. So you can press 1. You should be able to press enter too. I think I might have been in the wrong spot. But we're just going to choose that from the main matrix screen. You're not going to go to edit in this case. So I have matrix A times matrix B. So I need to go back to second inverse and choose matrix B. And so I have A times B, press enter, and we get this same 15, 43, 5, 17. So that's going to be how you can do it on the TI-84 calculator. Okay, so now I want to find the product of these two matrices. So the first thing I need to do is check the number of rows in my first matrix, which it has 2 rows, and check the number of columns in my second and make sure they're the same. So this one has 2 columns. And so then that means that my resultant matrix is also going to have 2 rows and 2 columns. So I'm going to go ahead and set that up and just kind of leave myself some blanks to work with here. And then in this one, it's going to take a little bit more to do it because in our rows, in the first one, we have 3 elements, and in our columns, in the second one, we have 3 elements. But that's okay. We just need to go through and find these. So for my position row 1, column 1 element, I need to look at row 1 in my first matrix and column 1 in my second matrix. So I need to multiply the terms that are in the same positions and then add all of our products. So I'm going to have 0 times 1 plus -1 times 4, and then plus -3 times 6. And I drew my box a little bit too small here, so I'm just going to erase this part and I'll expand it as I go. So that's going to be my first element. And then I'm going to go ahead and do row 2, column 1. So that'll give me this one here. So for row 2, column 1, I need 2 times -1 plus 1 times 4 plus 1 times 6. So I was multiplying my first term in my row times my first term in my column, my second term in my row times my second term in my column, and so on. Okay, so I moved everything over so I'd have more room to write. So now I'm going to start on my second column in my resultant matrix. So to find row 1, column 2, I'm going to use row 1 from my first, column 2 from my second. So I would have in this position 0 times 4 plus -1 times -4 plus -3 times -6. And then for row 2, column 2, I'm going to need to use row 2 from my first matrix times column 2 of my second. So for that one, I would have 2 times 4 plus 1 times -4 plus 1 times -6. And then that would end my matrix. And so I just need to simplify all of this now. So for row 1, column 1, I have 0 times 1 is going to be 0, plus -1 times 4 is going to be -4, plus -3 times 6 is going to be -18, and that's going to give me -22. For row 1, column 2, I have 0 times 4 is 0, plus 1, or -1 times -4 is going to be 4, plus -3 times -6 is going to be 18. So 4 plus 18 is going to give me +22. For row 2, column 1, I have 2 times -1 is -2, plus 1 times 4 is 4, plus 1 times 6 is 6. So that is going to give me 8. And then for my last element, I have 2 times 4 is 8, plus 1 times -4 is -4, plus 1 times -6 is -6. So if we add all of those together, that's going to give me -2. And this would be my product or my resultant matrix. Okay, I also realized I misspoke just a little bit whenever I was talking about the number of rows and number of columns. Whenever I was counting the number of rows in the first and the number of columns in the second, that was actually finding me the dimensions of the resultant matrix. But to be able to check and see if you can multiply them together, you would have to find the number of columns in the first, which is 3, and the number of rows in the second, which is also 3. So this is the check to see if you can multiply them. This gives you the new dimensions. So make sure that whenever you're doing that, to find the dimensions, you're looking at the rows in the first and the columns in the second. To find out if they actually multiply together, you're looking at the columns in the first and the rows in the second. Okay, so we're going to try this problem. So we're going to just look at the rows and columns in both. So the rows in the first is 2 and the columns is also 2. The rows in the second is 2 and the columns is 3. So to make sure that you can multiply them, I need to check the columns in the first and the rows in the second. And both of those are 2. So that's going to work out. So then my resultant matrix is going to be the rows in the first and the columns in the second. So my resultant is going to be a 2 by 3 matrix. So, and I'm going to leave plenty of space. I'm not going to try to draw the box yet for the actual multiplication process. I'm just going to draw one bracket for myself. Okay, so we know that this is going to have 2 rows and 3 columns. So to find my row 1, column 1, I need to be multiplying my first row in my first times my first column in my second. And I'm going to erase what we did here to determine if we could even multiply them together and to determine the dimensions so that I'm just focused on my row in my first and my first column in my second. So I'm going to have 2 times 3, and then I'm going to be adding that to negative 5 times 1. And then for my, I'm going to go ahead and do row 2, column 1. So I'm going to have 6 times 3, and then plus negative 4 times 1. And then I'm done with my first column. So I'm going to start fresh, and I want to do row 1, column 2. So for row 1, column 2, in my resultant matrix, I'm going to have 2 times 3 plus negative 5 times 3. And then I want to stay in column 2, and I want row 2 now. So for that, I'm going to have 6 times 3 plus negative 4 times 3. And now I just want to do my last column. So I'm going to have, well, I'm going to start with row 1, column 2, actually. So I'm going to have 2 times 3 plus negative 5 times negative 3. And then for row 2, column 3, I need 6 times 3 plus negative 4 times negative 3. And then that should give me my whole resultant matrix. So I just need to solve this out now. And so I'm going to write it up here. I just knew I didn't have enough room for all of this up here. So 2 times 3 is 6, and then plus negative 5. And that should just give me 1. 6 times 3 is going to be 18 plus negative 4. So that's going to give me 14 in row 2, column 1. And then 2 times 3 is going to be 6 plus negative 15 for negative 5 times 3. So that's going to give me negative 9. 6 times 3 is going to be 18 plus negative 12 is going to give me 6. 2 times 3 is going to be 6 plus negative 5 times negative 3. That's going to be a positive 15, so that's going to give me 21. And then 6 times 3 is 18 plus negative 4 times negative 3 is positive 12, and so that's going to give me 30. So this would be my answer to this problem. Now, for the sake of time, I'm not going to actually work all of these out, but I want you to pause the video and try to work them out on your own. I'm not going to make you watch me do it though. And then unpause whenever you're ready to see the answers. Okay, so go ahead and pause again and take a second to check your answers. If you got them incorrect, then see if you can go back and find where you went wrong. And if not, then you'll just have to ask me to go over these at some other time. So then I want to do one more example of finding the product, and then we have one more thing to do after that too. So the first thing that I want to do on this one is, again, find the columns and rows on both of them just to make sure we even can multiply them together. So the number of columns on the first one is 4. The rows is 2. The number of columns on the second one is 3, and the number of rows is 2. So we need to make sure that the number of columns matches the number of rows in the first and the second. And clearly 4 and 2 do not match. So when that happens, you're just going to say that this product is undefined. And if you had put that in a calculator, you would also get an error for that as well. So this is the last thing, so just hang on a little bit longer. There is something called the identity matrix, where in matrix multiplication, you can multiply by this matrix, and whatever your resultant matrix is, or your product, then that's going to be the same as whatever your original matrix was. So these are some examples of the identity matrix. Basically what happens is the diagonal is going to be all ones. And then any number that's not in the diagonal is just going to be a 0. So basically, that's how it's going to look. And then, like, typically whenever you think of an identity matrix, it's just like you're multiplying everything by 1. So you would think it would be filled with 1s, but that's not the case. So just be really careful of that and make sure that you know that it's the diagonals that need to be 1s. So then there's another note down here that if A is an m by n, so if it has m rows and n columns, then the identity matrix, depending on just like where, if you're multiplying the identity first and your original matrix second, or your original first and the identity second, then if you're doing the identity first, then it needs to have the same number of rows as your original. And if you're multiplying the original times the identity, then it needs to have the same number of columns as the original. So that's another situation where we were talking about matrix multiplication not being commutative. You just have to be sure that you have the correct number of rows and columns in your identity. And the identity matrix is also always going to be a square matrix, no matter what. So then this just goes through like how it works a little bit. So it gives you a matrix and then you're multiplying it by its identity. And you can do that by doing the original times the identity or the identity times the original. And you can see in here, depending on what order you're doing it in, is going to depend on how big your identity matrix is. Either way, whenever you do it, you end up with the same matrix, but it's just going to change because it's not commutative. So if you want to pause and read through this, then you can go ahead and do that now as well. And this was kind of our last thing, just find the product. So it gives you a matrix here, you're multiplying by a 2 by 2 identity matrix. And basically, if you see this identity matrix and it matches the correct dimensions, you can just go ahead and write down your original matrix. And that's going to be your answer. So I know this was a long video, and I know matrix multiplication is a really long process, but I do appreciate you hanging on and watching this and trying to figure it out and all the good things. So just let me know if you have any other questions about how to work out any of the problems, and please try the practice that I've posted as well. And that is really all for matrix multiplication.